Hello everyone. In this part of the lecture on steady-state analysis of closed-loop systems, we will have a look at the disturbance rejection. So we will see how a closed-loop system will deal with rejecting disturbances. For that, we will have a look at the expression that we have for the error term, E of S. As you can see it here, it is equal to S of S times R of S minus S of S times D of S plus T of S times N of S, where N is the noise, D is the disturbance, and R is the reference signal. And for the current topic, we are going to consider only the effect of D. Therefore, we will have E of S equal to minus S of S times D of S. So this will show the effect of the disturbance on the error term. And we will set N and R to 0. So this will be 0, this will be 0, because we are studying the effect of the disturbance only. But if you remember from the previous lecture, and you can see it also here as well, if we consider only the effect of the reference, or R, then we have E of S being equal to S of S times R of S. And now if you compare these two with each other, you can see that they are identical with the exception of this negative sign over here. Alright, so we will consider similar type of signals for the disturbance that we had for the reference. D of t will be in the form of t to the power of k over k factorial for k equal to 0, 1, and 2 for the step, ramp, and parabola kind of signals. And now since the difference in terms of the transfer function for the disturbance and the reference is in just a negative sign, so we have E over D equal to minus S and E over R equal to S. Because of the similarity that we have here, the behavior of the system in terms of rejecting the disturbance will be also similar, but with an opposite sign in it. Therefore, we can conclude our discussion over here. So if we have a unit step disturbance with k equal to 0, we can say that the steady state error, which is limit of E of t as t goes towards infinity, sometimes we show it in the form of ESS as well, will be obtained as minus 1 over 1 plus L tilde for type 0 system. So, and you should remember that in the case of type 0 systems, we don't have any pole at the origin. And it will be 0 for type 1 and higher type systems. L tilde over here will be equal to limit of L of S as S goes towards 0. And again, L of S is the loop transfer function, which is type 0, so it doesn't have any pole at the origin, and as a result, this limit that we have here will give us some finite value. If you have a type 1 system, type 2 system, and so on and so forth, the steady state error for the unit step disturbance will be equal to 0. On the other hand, for the unit ramp disturbance, when k is equal to 1, the steady state error for type 0 systems will be equal to minus infinity. Pay attention to these negative signs here and there. For the type 1 system, we will have it in the form of minus 1 over L tilde. And again, L tilde here will be equal to limit of S times L of S as S goes towards 0. Since we have a type 1 system, this will be some finite value. And then for the type 2 systems or higher, we will have the steady state error equal to 0, similar to the case of having it for the reference signals. And finally, for the parabola disturbance input, for the unit parabola where we have k equal to 2, for type 0 and type 1 systems, the steady state error will be equal to minus infinity. Pay attention to the negative sign. And then for type 2 systems, we will have it in the form of minus 1 over L tilde, where L tilde in this case is equal to limit of s squared L of s as s goes towards 0, and this will be some finite value because we have a type 2 system. And if the type of the system increases, the steady state error will become equal to 0. Okay, so that's all about how the closed loop system will behave in terms of rejecting the disturbance. In the next video lecture, we will go through 2 examples where we have some transfer functions given for the controller and the plant, and also a set of given reference signals for the disturbance, and then we will see what happens to the steady state error of the system. Thank you for watching this video.